मैम वापिस मैम का कीबोर्ड नहीं चल रहा। हेलो मैम का कीबोर्ड नहीं चल रहा है, क्या इशू है?
Good afternoon. Good afternoon. We start the sixth lecture in this series, that is Statistics in Research Methodology. We have a quick recap of all the discussions till date. We had discussed the importance of statistics in daily life as well as research further. We understood the parameters, physical quantities, and the factors affecting the measurement of these physical quantities. For the results, how to present the results in the appropriate way, accuracy and precision of measurements, significant figures, place value of digits and rounding off, and the rules pertaining to each of these factors. Then further, we had gone ahead with error propagation rules and types of different categories of measurement errors, namely gross, systematic, and random errors, and the ways to tackle if at all we encounter such type of errors during measurement. In order to understand the characteristics of repeated measurements, we have understood the details of Gaussian distribution function and applied for repeated measurements during our research. Further, confidence levels, confidence intervals, and confidence limits of repeated measurements are also discussed in the previous class. Next slide. So, in the last slide of previous lecture, one question was given to all of you as an exercise, wherein you had to find out which curve is having the most precise and accurate measurement, and the one having systematic error. The ways to tackle systematic error, at least one method you should write. Then arrange these curves in the order of increasing precision, and which curve is more acceptable between the two yellow and green curves. The answers to each and every question is given here. The blue curve is having the most precise and accurate measurement among all the four. This can be visibly read from the curve as well as the numerical value of mu and sigma square given as inserts in the figure. Those curves which fall exactly where mu is equal to 0 and whichever has got a smaller value of sigma square, that is having the most accurate and the most precise measurements. Hence, the blue curve is the one which represents the accurate and precise measurement. For understanding systematic error, one has to see whether there is a shift in the position of the curve with respect to the mu equal to 0 value. So that is the green curve. And in order to address a systematic error, one can do the calibration of the measuring equipment and proceed further. When you arrange the curves in the increasing order of precision, what will happen there? Sigma square, you have to see the sigma square. If you are seeing the numerical values, the smaller the sigma square, the better is the precision. So start from the highest value of variance to the lowest value of variance. So that way you can simply read through the numerical value, or else through the graph. It will be yellow, red, green, and blue. So the blue one will have the highest precision. Then if you compare between the green and yellow curve, green curve has got a systematic error, whereas the yellow curve is does not having any systematic error. However, the precision is very poor. So the better way, if at all given a choice, it will be the green curve. We will go ahead because systematic errors can very well be addressed and completely eliminated. So the green curve, whichever experimental is producing, he or she can be relied upon. Then the systematic error can be addressed and it can be made equal to the mu value equal to 0, so that you can get reliable data. Reliability is essentially the improved precision. Next. Okay. Now, we have already learned the properties of the normal or Gaussian distribution function. Furthermore, two more similar distribution functions we will discuss today, because these are the ones encountered quite frequently during the analysis of repeated measurements. If you go to literature, you will see several similar types of continuous probability distribution functions. But since these are the most frequently encountered ones, we discuss these two additional ones. One is the uniform or rectangular distribution, wherein the probability of occurrence of each data given in the curve is equal. Probability is equal. So it is called a uniform probability distribution. The third one is a triangular distribution, wherein you get sharp decrease compared to the Gaussian curve. You get sharp decrease as we move away from the mean position. When we do apply statistical analysis, we essentially look for the parameters mean as well as variance. Variance is nothing but the square of standard deviation. So mean and standard deviation, or essentially the variance. These are the parameters we look for. We had used these properties of the Gaussian curve for explaining the observations occurred during the repeated measurements. So these are tabulated here, mean as well as variance, for all the three different continuous probability distribution functions. Mean is the central position in the symmetric curve of the Gaussian curve. If you calculate the mean for a rectangular distribution, it will be average of the values obtained on either extremes of the horizontal axis, that is half a plus b. Similar will be the mean for the triangular distribution, also half a plus b. Variance, while calculating the variance, here we have to define one term called d. That is nothing but here the d value is taken such that if you move plus 3 sigma on right side and minus 3 sigma, that's 3 sigma on the lower side. So that means total, if you move 6 sigma from my negative extreme to the highest extreme, you will be covering around 99.73% of the entire area under the curve for a Gaussian distribution that we had discussed in detail in the previous class. If you take 3 sigma on either side of the mean value, 99.73% of the total area under the curve is covered. So these extremities, confidence limits, lower and upper confidence limits of Gaussian curve are called the plus and minus d, plus and minus d. Okay, that is nothing but mu plus 3 sigma and mu minus 3 sigma. So if you want to calculate the standard deviation for that one, it will be nothing but square root of d square by 9. That is d by 3. That will be the standard deviation for a Gaussian distribution function. Similarly, for a rectangular distribution having the half width of around d on either side, you will see that the variance will be d square by 3. Corresponding standard deviation will be d by root 3. If you are to normalize with respect to Gaussian curve for the other two, the variance is to be taken care of in this way. Variances are comparable when you take the d values of these three different functions and calculate, then you will see that d square by 9 for Gaussian function will be equal to d square by 3 for the rectangular function. And if you apply the same principle for triangular distribution function, you will see that the variance will be corresponding to d square by 6. If you have to take the standard deviation, take the square root. And the examples of each category of repeated distributions, repeated measurements are given here. Gaussian distribution we have very well discussed in the previous class. Any natural variable, if you start measuring n number of repeated readings, you will see that it follows a normal distribution function. If at all you use a measuring cylinder which is not properly calibrated, the normal laboratory there, you will see that there is fluctuation in the measurement because the reliability is poor. Similarly, if at all there is any device or a tool which is not carrying any certificate, that means it is not very well calibrated, you will see that such measuring devices will lead to results of measurement which follow a rectangular type of distribution. Probability of occurrence of extreme values will be equivalent to that for the central value. There are a class of glass wires or volumetric wires which stand in between both these extremes, either natural probability or the rectangular probability. So these categories of vessels are called following triangular distribution function. There, in order to neutralize the effects, what we do is if you are calculating the standard deviation, the value obtained in the its certificate is divided by square root of 6. So that way we normalize the values and then compare the results further ahead. This contribution from different types of probability distribution functions are utilized when you do the propagation of uncertainty and land up in the final results, wherein you do a normalization of individual contributors. This slide is for just completion of the discussion. Normally, when we do repeated measurements of infinite number of data, you will see that those follow continuous probability distribution functions. But there are a few examples like tossing a coin and all. There you have finite number of outcomes expected, then it follows discrete probability distributions. No, generally, these three categories listed over here in the table, binomial, Poisson, and Bernoulli distributions, will suffice for the discussion regarding statistical analysis of data. So that much only is included here. When we address a data using statistical principles, we look for the mean and variance. The mean and variance formula are given on the rightmost columns, 2 columns on this table on the top, where the parameters, input parameters in the functions, in the n represents the total number of trials when you are doing repeated measurements, and P represents the success probability for each of such trials, and Ex is the predictor probability for exactly X such successes. Okay. And keep in mind that these discrete probability distributions are defined for integer values only, as we discussed in the very first class. And binomial function is a generalized function. When we apply some limiting conditions to that function, we can approximate it to the other two functions like Poisson and Bernoulli function. Poisson function can be applied for those type of measurements where the success probability is very small, almost close to 0. Success probability is almost close to 0, and the number of repeated such trials are very large. Then the Poisson distribution function is easily applicable. One such example is the measurement of radioactivity during analytical measurements. And the Bernoulli function is a special case of the same general binomial distribution when the number of trials is limited to a finite value of 1. In this slide, one example is there to show you if we calculate using 2 different distribution functions for a particular data, what will be the outcome? For example, if somebody is manufacturing tools for a certain process and 10% of that total manufactured tools are found to be defective, that is the general observation. If at all you are choosing randomly such tools, if from among 10 such tools selected, what is the probability that exactly 2 of the 10 will be defective? We can use either the binomial or the Poisson distribution function, the probability distribution, and calculate the probability. Okay. Then you will see that the equations given in the previous slides are simply substituted for each of the values, n as well as x and p. All the values are given. Just substitute in this equation, wherein lambda is nothing but the product of the total such trials and success probability n into p for the Poisson distribution function. Lambda is a particular further parameters. And you see that if you calculate via 2 different models, there is a slight difference in the second decimal. For the binomial, you got 0.19, whereas for Poisson, you got 0.18. Because there are some certain limiting conditions for each of these factors. Binomial is a general one. It follows that whenever we do repeated measurements, always experimental results are not found to be exactly matching with the predicted one. They seldom agree with the predicted theoretical models. Theoretical models are predicted for the ideal situations, whereas natural variables will have their own inherent fluctuations, which will result in sometimes on either side, on higher side or lower side fluctuation, which may slightly affect the accuracy also. Precision will be poor, definitely. Slightly it is taking away. That slight movement is nothing but the systematic error which can be properly addressed and nullified. But we have to keep in mind that natural variables, when we do repeated measurements, there is a finite probability that you will be reaching a value slightly different from the expected one. So what happens as a result, we always have to judge whether there is a numerical difference in the results of a real analysis and the theoretically predicted outcome. Definitely, one has to address these problems. So statistical tests will be helpful in sharpening the judgment of such results and coming out with the useful inferences from the measured data. So what we normally do is we propose some theory that the experimental results will be so and so. And accordingly, we give some substantiating theory also. Finally, once we come out with the results of experimental data, we verify whether the measured data is matching with the predicted one. That means experimental and theoretical values, whether they are matching or not. Initially, we propose that they will match definitely, that then only we start the experiment. And then we hypothesize that both are having same distribution, both will have the same value. Ultimately, when we land up in the final results, experimental results, sometimes, most of the times you may see that there is some slight variation. Herein we do the statistical hypothesis testing and try to arrive at what could be the cause of that variation, whether that can be addressed by understanding the theory behind these observed variations. That is called the testing of a hypothesis. Initially, we propose that the theoretical and experimental values should match. And finally, after doing the experiment, you analyze the data, re-verify the data, and if at all they are very well matching, then we go ahead with that set of results. If at all if it is not matching, we may change the hypothesis. Then we may go for another hypothesis, second set of hypothesis. Then again, revalidate the experimental data by comparing with the proposed model. That way we do iteration, and finally we have theoretical backing for the experimental data. That way we come out with the results and explanation for whatever is observed during laboratory experiments. So when the theoretical data and experimental values match very well, then it leads to the formation of a useful theory until a situation arises where someone else or some other theory is refuting this one. Till that point, the theoretical model, experimental data go along with together and form a theory which can be the basis for further future planning and design of experiments. Okay. So during this testing of models, we do the analysis of data, experimental data, which we call as hypothesis testing. For this, we initially propose that the observed quantities, it may be either the agreement between two or more observed quantities, or sometimes it may be the agreement between observed quantity and the predicted value, predicted theoretical value. Sometimes it may be a threshold value. Sometimes it may be a specification, upper limit of a specification, or sometimes lower limit of a specification. If it is a theoretical model, then most of the time, as somebody was asking in the previous class, if it is a theoretical model wherein you do not have any prior knowledge about the data, you anticipate the data to fluctuate on both higher and lower side. So you do two-tailed testing. If at all there is like a threshold value or a specification limit which hinders the value to go on either higher side, then definitely you will have a single tail, uni-tail, one-tailed test. We will discuss those things in detail in the further slides. So generally the terminology is like this. The initial hypothesis or the postulate that the theoretical value and the experimental value match very well with each other, it is called the null hypothesis. Okay. In the null hypothesis, we presume that the numerical quantities being compared are in fact the same. Okay. Then we use the probability distribution functions as per the requirement, whether it is a continuous or a discrete probability distribution function. We apply the required formula and calculate the probability that the observed differences are due to random error or due to any systematic error. Systematic errors, very well, we do separate analysis by doing the outlier or the systematic variation in the instrumental fluctuation, calibration, or standard reference material analysis and all. So that can be very well done. Generally, what we do address is the random error. Okay. If the difference between the measured value or the experimental value and the theoretical value is larger, when I say larger, in terms of numerical value, it will be, for example, if I do 100 repeated measurements, more than 5 times I get a difference, large difference between the theoretical and experimental values, then I say that the probability of occurrence of two different sets of data is large. There is a significant difference, significant mismatch between the theoretical and experimental values. 5 out of 100 repeated such trials, if you are getting values which are far apart from theory as well as experiment. We are comparing theoretical value and experimental value. 5 out of such 100 repeated comparisons, if you are getting larger values, larger difference, we say that there is a significant or substantial difference between these two values. They are belonging to two different classes or two different sets of data. That means your null hypothesis should be rejected. Normally, whether to reject or accept the null hypothesis, that is a question we address during statistical analysis of data. This type of analysis we do at the end of the experiments. Once you do acquire knowledge regarding the difference, significant difference, or the rejection of null hypothesis, next time when you formulate an experiment, you propose a hypothesis in such a way that whatever negligence or error you committed in this comparison is taken care of, so that each and every next trial you are brushing up the data, improving the data, and coming out with the better and better quality results. So that way you develop the skill also. So each and every time you do apply a different procedure or a methodology, do this significance testing or null hypothesis application, then modify if required. If not required, then you can go ahead with the presently obtained experimental data. As we discussed in the previous class also, significance level, if it is expressed in as a fraction, which is between 0 and 1, the symbol alpha is given. If it is expressed as percentage, we call as probability also sometimes, probability of occurrence. Some designation, you will see that P, the capital P is given for defining the significance level when you express as percentage. Okay. The confidence level is nothing but the difference between 100 and the percentage significance level. Otherwise, 1 minus alpha. That is confidence level. These terminologies you should be familiar so that when you use the T tables, the statistical tables, you can read through the tables easily. The proposition that your experimental data is whether it is matching with the theoretical data or not, that is done in two different ways. One way is to apply the null hypothesis. Generally, that is the initial, first and foremost procedure. We state that two measured quantities are identical or equal. That means mu is equal to mu 0. Mu is the measured one, mu 0 is the reference one or the theoretically predicted one. So if mu and mu 0 are equal, that will be the null hypothesis for most of the time, if not mentioned generally. The alternative hypothesis is that mu is not equal to mu 0. The measured value is different from the theoretical value. Alternative hypothesis can be proposed in other ways also. For example, if you are looking for a higher upper tailed this thing, category of statistical data analysis, then alternate hypothesis will have the form of mu greater than mu 0. If it is a lower tail, it will be like mu less than mu 0. There are three different forms or representation of alternative hypothesis: mu not equal to 0, or that will represent the two-tailed category, mu greater than mu 0, or mu less than mu 0. So one example is given here. Two such examples are given here so that you can understand the difference between these two categories. Okay. If we are determining the concentration of lead in an industrial effluent water stream, and there is a specification limit of 0.05 ppm. If at all the maximum limit is exceeding, then you have to take precautions to reduce the lead content in that effluent. Okay. Here in the hypothesis would be, if in random measurements of the effluent water quality, the mu value, measured average value, if the mu value is equal to 0.05 ppm, that means the null hypothesis is satisfied. Mu is equal to mu 0. Then here the testing, hypothesis testing should be done for all those categories wherein the mu value is greater than 0.05 ppm, so that you can take a decision upon whether this industry is following the conditions of limiting the lead content in the water to be less than 0.05 ppm. Here you have to apply a one-tail test. There is an upper limit of specification. You have to see whether the value is exceeding the limit or not. So this is one case where one-tailed test is only applicable. The second one, second one is an example where you apply the two-tailed test. If, say, for example, when somebody is randomly measuring the water lead level in the water for over a period of several years, and they report a value of 0.02 ppm. And in one year, if at all they expect a variation, which may be either on the higher side or lower side, still it is an effluent, then whether it is coming within the average of several repeated measurements earlier or not, the value may lie on either side of the mean value. Here you have to apply the two-tailed test. If at all there, just by reading the question or the problem, you can make out whether you have to apply one-tail or two-tailed test. These are all regarding the testing of hypothesis. Hypothesis generally starts with the null hypothesis, wherein you say that the data obtained in two sets or two models are identical. That is the null hypothesis. If at all there is a difference, that proposition we call as alternative hypothesis. There are three different cases or different examples wherein this hypothesis testing is generally done. One is that you are comparing the experimental data with the true value or the known value or the predicted value or the model value. These are the different terminologies for the true value: known, assigned value or model value, or the predicted value. Or you can compare the value obtained by one particular set of measurement to a threshold value. Definitely when you do compare with a threshold or a cutoff value, it will be undergoing one-tail test. When you can compare the standard deviations obtained from two different procedures or two different sets of methods, maybe two different experimentalists or two different laboratories, two different instruments, that time you do two-tailed test of significance or two-tailed test of hypothesis. Okay. In order to do this hypothesis testing, you have to follow systematic steps. First, you have to construct what type of test we have to conduct, whether you have sufficient number of data available with you. If not, collect that data and start the accumulating under each category and apply the test. Okay. And identification of the appropriate tool for a particular hypothesis testing is very important. After this lecture, you all will be equipped in which case we have to apply a particular test. Whatever we do discuss is the Z test and T test in today's class. Furthermore, we will do the other tests in the coming classes. So where to apply which test, that you will be equipped, you will be able to decide upon independently after this discussion. And the null hypothesis generally has a form that two values obtained by 2 are identical. And after the testing, if the calculated value of your parameter, say the t statistic or the z statistic, if whatever you do apply for your experimental data and theoretical data, or sometimes experimental and threshold value, or maybe between two independent experimentalists, if the calculated value of the statistic is coming out to be less than the corresponding critical value or the tabulated value, when we do this hypothesis testing, generally we rely upon statistical tables reported in the literature or textbook or the web references. If at all the calculated value is less than the tabulated value, then we accept the null hypothesis and say that the data being compared, the set of data being compared are identical. We can go ahead with the present data set of results and do further analysis or further inferences. If at all the calculated p-value comes out, calculated statistic, whether it is t or z or any other statistic, then if it is coming out to be greater than the critical value, then we reject the null hypothesis and say that the values are not identical as far as the statistical analysis is concerned. That means they are different. Their difference may not be only due to random variation. There may be some systematic error, or there may be an actual difference or in agreement between the two sets of data. One has to revisit and get to a conclusion whether it is due to any systematic error or is it due to an actual factual difference between the two sets of data. So rejection of the null hypothesis, the procedure steps goes increasing. If at all you accept the null hypothesis, the statistical analysis is done, you can go directly to the inference. Now we come to the Z statistic and then we go ahead for the T statistic. The Z statistic slightly we got introduced in the previous class wherein we had learned regarding the Gaussian distribution function of natural variables and the standard normal probability curve where the parameter Z was defined. That is nothing but x minus mu by sigma. X is the measured value, mu is the mean value, sigma is a standard deviation. Okay, x minus mu by sigma. Whenever sigma is not known, we go for another test statistic called T statistic that we will discuss in detail today, and we will have a comparison between when to do T, when to do Z. If you have any unknown or dark spot or blind spot in your analysis, if you have only limited number of data points with you, go for T statistic. T statistic is a superset which will include all the parameters, all the variations, random variations during your measurement. Students T statistic and its testing hypothesis testing procedures we will discuss now. The T statistics is given in the equations over here on the left side blue colored box. If you are comparing one particular experimental data X, it's either the theoretical value or the predicted value mu, and you have the standard deviation S for your measurement, you can have the T value as x minus mu by S. When you do replace x with x bar, that is mean of repeated measurements, the standard deviation also gets narrowed down to S by root n. So that way the equation for T gets slightly modified when you do compare mean of repeated measurements with the reference value of mu. Once you calculate the T value for a set of data and compare with the mu value, what you normally do is take reference to the corresponding T value in the literature reported values in the table. As we had seen in the previous class for the Z values, probability distribution function, the T values also we have literature data wherein the number of measurements n and another term called degree of freedom is defined. Degree of freedom is nothing but the number of terms required to define a system completely. if we have n repeated measurements and there is a stern relationship between the n repeated measurements and the mean x bar, the number of degrees of freedom will be n minus 1. And the significance level or the confidence level. As I told you, confidence level we have defined depending on the width of the baseline of the distribution curve. 1 minus confidence level is nothing but significance level alpha. Then you read the t-value from the table corresponding to the number of degrees of freedom from top to bottom. I will show you the table and you all will be able to read through that. Then go for the significance level or the confidence level. Everything is written in the legend of the table. First, whenever you read any table or a figure from internet or a textbook or any literature reference, read through the legend properly, then only apply it to your situation. And confidence interval is also defined in terms of t-value over here. That is nothing but x bar plus minus ts by root, and when you replace x bar with x, it will be x bar plus minus ts. Root n will not be there. The probability distribution function t is given by this function as we have seen for the Gaussian function. Similar mathematical expression is there and the sigma value, the standard deviation for t distribution, as it generally applies for mean of repeated measurements, you can see that it will be sigma by root n. Here is the general form of the t table. This is an inclusive term for inclusive table for both one tail as well as two-tailed table. You can read through the legend of the table. The table is given in the left side of the screen. Cumulative means cumulative probability for a t function, and if you are reading through the table, degrees of freedoms are mentioned on the leftmost column of this table. If you have, say, 10 number of repeated measurements, degrees of freedom will be 9. Degrees of freedom will be 9. Okay. And depending on the confidence level, as I told you in the previous class, if the confidence levels are not mentioned, general intuition is that go for 95% confidence level. That is nothing but 0.05 alpha. If I am looking for 10 number of repeated measurements, I will go through, say, 95% confidence level. It will be coming out to be 2.262. 2.262 will be the value for t corresponding to 10 number of repeated measurements, wherein the degrees of freedom is 9. So all of you have a practice on reading this t table, degrees of freedom and the significance level. Here in the table of t distribution curve, the values of z are also given in the last row. If you compare the z values and the t values, you can see that as the degrees of freedom increase from 1 to 100 to 1000, as the degrees of freedom increases, the t values start getting smaller and smaller, getting reduced, and finally they will almost approach the values of corresponding z for a particular level of confidence. So that way one can have an estimate of whether you are doing the proper way or not. This one-sided and two-sided test we have discussed in detail till now. One-sided test is done for such previously known category of experiments wherein you expect or anticipate only one particular set of deviation from the real value. And generally, if not mentioned, we go for the two-tailed test. So that way, accordingly, you have to read through the two-tailed test. If you are going for two-tailed test at this 0.05% significance level, for 9 degrees of freedom, you have the value of 2.262. Corresponding one tail value will be 0.025, the same. For a given value of n and a particular probability level, the critical value of one-sided test will be definitely different from that one for the two-sided test. Okay. Here, the examples are given over here. If you compare for a one-tail test, having significance level of 0.05 for the same degrees of freedom of 5, the value is 2.015. For significance level of 0.1, that means when you go for two-tailed test, the double the significance level because it is symmetrically distributed on either side. So the value of t corresponding to a particular significance level will be matching with 2 times significance level for the respective two-tailed test. So when we do not have sigma in hand, how to define the confidence level? Then we normally go for t-test and apply the correction factor. Confidence level is to give a range of the values within which the true value is expected to lie with reference to the measured values. And most of the time when we do in laboratories, we do only limited number of repeated measurements. So you will see that generally the t-test is applied in practical cases most of the time, unless you are a nodal agency comparing the values of huge number of data points, or maybe you are a population scientist, you will have large number of data, or an environmental scientist where you have accumulated enough number of data, more than 30 number of data, then Z tables, Z distribution functions are applied. Laboratory physicists and chemists, normally we do go for limited number of repeated measurements. In the other coming classes, we will see what we are going to gain by repeating number of measurements or a particular quantity by similar set of reproducible measurement. What is the improvement in precision you are going to gain by repeated measurement? That we will see in the next class. If at all the data are independent of each other, definitely the more the number of data, the better will be the precision. But if a same quantity is being repeatedly measured, though you will be gaining in terms of precision, whether it will be substantial or visibly different from the other one, that we will see. Now that we have understood two different types of tests, Z and 2 tests, when to apply which test, that contexts are given over here. When we have large number of data points, when we know the population mean and the standard deviation of the entire population, Z tables are used, Z tests are used. When we have limited number of data and the population variance and the population means are not in our hand, it may have fluctuations, it is not predictable, then we go for t-test. So most of the practical cases, you will see that t-tests are applied, and when the degrees of freedom approaches large quantities, definitely t values will go and get merged with the Z values. So there is no harm in applying t-test even if you have larger number of data, because they will go hand in hand at larger extent. It is better than, though it is involved calculation nowadays, computers or calculators or software packages are available to do this. You have to only feed in the experimental data, the entire calculations will be done. You can get the inference, but keep in mind that have a cross check with the whatever data is given by the computer manually also. Once in a while, have a cross check. So if you compare the data distribution for repeated measurements for T and Z values, the green one, which is having narrower distribution with a smaller tail, that represents the standard normal probability distribution, that is the Z curve. When you have limited number of repeated measurements, you will see that the purple, blue, and the orange color curves are obtained. As we increase the number of data points or number of degrees of freedom, you will see that the tail portions get lower down and the curve becomes more and more narrower and reaching almost comparable to that of the green curve. Ideal situation will be with limited number of data points, you are able to mimic the green curve, which is almost impossible in real cases. When we have infinite number of data points, the degrees of freedom, when we represent t values, the lowercase letter t is used, degrees of freedom is mentioned, then the significance level, these two degrees of freedom significance levels are mentioned as subscript on the right side of that value. In the case of wizard, normally it is a normal distribution curve. So you will have infinite number of degrees of freedom. So degrees of freedoms are not mentioned. And the area under the probability curve will be given by the value of the z, as we have seen in the previous day's discussion. As the sample size increases and approaches infinity, you just have seen that the T probability curve also mimics the Z probability curve. Okay. These are the different case contexts where we compare the experimental mean with a known value. There are many cases in which scientists or engineers need to compare the mean of a set of data with a known value. If the known value or true value is there with us, then we can have a comparison. And if you have the sigma of the known value, you can go ahead with the Z test. One such example is the comparison of the measured values of cholesterol to the values certified by NIST. NIST is National Institute of Standards and Engineering in a reference sample. Here you can do the Z test. Directly you can do because you have the reference value with you and you have lot of number of data points available. Sometimes the known value is predicted from the theory or it may be due to some threshold value. Then we do one-sided test of Z if provided the data is having infinite contributors. Then we go for Z test with the one-sided distribution. We had seen one-sided, two-sided symmetrical distribution of Z table also. In all these cases, a statistical hypothesis testing is helpful to us to take conclusion from the observed mean value and its nearness to the known or the accurate value of mu zero. When we have, as we discussed in the previous slide, if we have large number of data points, we go for Z test. The Z statistic has the formula x bar minus mu zero by sigma by root n. X bar is the mean of your measurements. Mu zero is the referred value. Sigma is the population standard deviation. N is the total number of measurements. As we discussed earlier repeatedly, the null hypothesis is mu is equal to mu zero. Alternative hypothesis can take either of the three forms given here. First one is the two-tailed representation. Second one is single tail and the upper tail. One tail with the upper portion. And the third one is the lower one-tailed test. The formation and the comparison is given here. If you go for two-tailed test, the table which you are referring to for the Z values will have a form which is given on the top left side of the three figures. Top left side figure, that is the general representation of two-tailed Z test. Middle one is the upper one-tailed one and the rightmost one is the lower one-tailed one. These all three types of figures we had discussed in the previous class. As you can see, two-tailed one, we will have symmetrical distribution on either side. So the significance level will be double that for the corresponding single-tailed one. That way, you have to read through the table. In the table legends, it is very well explicitly written. You have to be careful reading through the Z table. This is just to show you the same thing, whatever is written in this slide. At 95% confidence level, what is the Z value for a one-tail test and the two-tail test? The values are given here. 0.4750 will be for the double-sided one, 1.96. Z corresponding to 1.96. When you have the single tail, it will be 0.4495 corresponding to 1.64 sigma. Z value corresponding to 1.64. This table is the same which we discussed in the previous class, just showing you at 95% confidence level, one-sided tail value and the two-sided tail value. One-sided tail value is 0.4495 area and two-sided it is 0.475. Then you have on either side multiply with 2. When you have limited number of repeated measurements, we go for t-test. The equation gets slightly modified because sigma is not known to us. T-value we calculate. When we calculate the t-value, we will be comparing the calculated t-value with the corresponding t-value for those in the table. Here, instead of repeated measurements, we go for the degrees of freedom. That is one most important thing we have to see. Instead of repeated measurements, go for the number of degrees of freedom. That is nothing but one number less than the total number of measurements. The null alternative hypothesis formula remain almost comparable when the calculated t-value is equal to is less than the critical t-value, we accept the null hypothesis. If at all it is greater than the critical t-value, we say that we reject the null hypothesis and go ahead with the alternative hypothesis. That means whatever we predicted is not going to follow. You may have to modify your experiment or you may have to have different procedure to get your values. Or if you are comparing between two means, that means two different ways have made you reach two different targets. That means the procedures you have adopted are not similarly applicable for a particular context. This curve is the representation showing the outcome of two experimentalists A and B. They have got two different sets of data. You can easily understand that the curve A, which is on the left side when you are viewing the screen, it is having a mean value which is exactly matching with the mu zero. That means there is no bias, there is no systematic error in the case of curve A. Whereas in curve B, you will see that there is a positive shift in the value. So bias is there, which has got a positive magnitude. That is nothing but the difference between mu B and the sigma mu zero. So the curve B is having systematic error, whereas curve A does not have. So this just visibly by seeing the curve you can make out. Alternatively, you can apply the t-test and mathematically evaluate and come out with the same result even without seeing the curve. T-test for significant difference or systematic error in two set of measurements. Taking one as a reference, you will be able to have a comment on the systematic error of one set of data obtained by different experimentalists. So from the t-test also we can infer that curve B constructed by the experimentalist is having some systematic error. The equations also I will show. T-test can be used for comparing two experimental means or understanding the differences between two means. Okay. If you have to compare two experimental means, you should have the mean value along with their standard deviations also. If the standard deviations are comparable, then you can go ahead with the comparable standard deviation and use a formula called pooled standard deviation formula for t-test. If at all they are having different standard deviations in magnitude which are not comparable, then you have to evaluate them separately and come out with the observation and conclusion. Here again, the null and alternate hypothesis have the similar form as we discussed for the Z value also. When we are comparing one mean with a reference value of say mu, x bar with mu, here again we can do the t distribution formula and calculate the t value, then compare with the corresponding t value in the table for the respective number of degrees of freedom as well as the significance level. If the calculated t value comes out to be less than the tabulated t value, you infer that the mean is observed mean, experimental mean is almost statistically equivalent to the theoretical mean or the actual value. If at all the two means being compared, one is not the reference value, it will, the second mean also will have a finite standard deviation rather than the sigma. Then the formula gets accordingly modified. These, in nowadays, people use computers or softwares to do all these calculations. One has to initially define whether you are going to give input as mu or x bar and y bar. Accordingly, the input parameters also you have to give. You can give the S standard deviation, number of degrees, number of measurements. Accordingly, the t value will automatically be taken out from the statistical tables. There are different categories as discussed. This is the last slide of the day. This summarizes the different types of t-tests to be carried out depending on the occasion. One sample, two sample, or paired t-test. This slide we will discuss in detail in the coming day. If there is any clarification required, we will discuss now. This slide we will restart in the next class. Let us go to the chat box and see if at all there is any clarification or suggestion or discussion. Otherwise, I will summarize. While going through the chat box, I will summarize. We have discussed the different types of distributions, continuous and discrete probability distributions in the beginning of today's class. Then we had gone ahead for testing of hypothesis, proposition of null hypothesis, alternative hypothesis, and comparison between experimental and theoretical values. Then comparison between an experimental and a threshold value, comparison between two experimental means or the difference between two experimental means, when to use the Z table, when to use the Z test, when to use the T test. These are the things we discussed today. The other class we will go for T test and the different categories of T test and get a practice, hands-on practice on utilization of the T table in the coming class. These are the simplest of the statistical hypothesis testing. Z table, as you are all familiar, as we discussed in the previous class. Today we got introduced to the T table also and hypothesis testing via the T. These are the simplest of several hypothesis testing. If there is no doubt, we will wind up for the day. No doubts are seen. Then we will discuss on 11th, Friday, the remaining portion. Is there any doubt here? You need to. Maybe towards the end they normally do. Initially they have the attendance. If there are no doubts, let us leave.